Alright, should be making a video. Live video. At the moment that I'm making it, it appears to be that way. And such. So, do this little preliminary crap and such. Alright, good enough. So the opposers, I don't know what else to call them. I guess we should come up with some sort of name for them. You know, the little Brozo's little happy troop of morons. But anyway, the Ian Gosling, Ian, has made another, you know, just doubling down on his completely unreverenced. I mean,
there's less weight.
Doesn't in any way say anything
Last video
about how it could possibly be true. Okay, well, he's just going to talk about this skier who cares, the old, what he did before. Now he's just dragging bricks on a treadmill and measuring how hard, how much pressure you have to apply to the bricks to get them to slide across the treadmill. And he says, you know, this somehow undoes the 500-year-old Galilean principle somehow. No,
types of friction. And the last tests showed that it was largely independent.
So he says it's largely independent. He's measuring with a really crappy scale. So it's obviously, I would argue, it's not independent. You can change the circumstance, change it into sandpaper or something, and rub it against a block of wood, and you could expect to make a lot more sawdust, you could argue.
The pulling force was independent of the velocity.
So it doesn't mean anything. The pulling force is independent of the velocity. Obviously, if you try to give the object momentum, so if the conveyor belt wasn't moving at a constant velocity and you had to push the bricks and make them go, there wouldn't be any idea that somehow it's the same amount of friction. That is, if I put less energy in, I'll get less and less and less distance. We already know what the outcome is going to be. The faster you go, if I double the speed, I'll get 4 times the distance. We already know the rules. So it's, you know, to say it's constant, it can't be constant if you can vary how far you can go.
Of its movement over the road.
Okay, over the road. So it's not moving over the road's moving under it. So completely different experiment, right? I mean, so I'll go over this again. I'll just play the rest of this crap and we'll get through it, and then I'll
because it makes
redraw
no
all the same arguments.
Whether you're pulling this car, pushing of the car.
So he's just said it doesn't make any difference. So let me play that part again, sorry.
Of its movement over the road. Because it makes no difference whether the...
So he's saying it makes no difference. It doesn't matter which object, or so it's some sort of equivalency principle he's saying. So moving a conveyor belt at a constant velocity is the same as moving the blocks at a constant velocity. So that would be like saying it goes 4 times further when it's at a constant velocity. No, it doesn't do that. It only goes 4 times further when you're extracting the energy. So when you're fighting it. So if you go at a constant velocity in gravity, okay, you won't go 4 times higher. There's all the rules break because you're not dealing with actual circumstance, because you're compensating your velocity to how much resistance there is. So by having the conveyor belt go twice the velocity, you know, breaks the experiment in the sense that you'd only expect now. If I was to push the block at a constant velocity, I'll guarantee that the twice as fast block goes twice as far, not 4 times as far. So I'll guarantee, okay, that your math won't work, that your theory won't show itself. Okay, it's a guaranteed fact that if I go at constant velocity, there's no evidence of your 4 times the energy. You're only going to go twice as far, but you're also not extracting the energy. So that's the whole point. So, I mean, there's just no thought in anything they do. And so, you know, for all the critics who say, oh, you're implying a conspiracy theory. Well, isn't this a kind of conspiracy? They're contriving any kind of perverse way to do the experiment. You know, drop the round objects into the clay. You know, put the block on a conveyor belt because you can confuse somebody if you do this. we can confuse the experiment by moving the road instead of moving the cart, and applying a constant velocity which breaks all the rules anyway. The same rules don't apply when it has a constant velocity.
Whether you're pulling this car, pushing the car on a stationary road.
Right. So yes, you're right. It doesn't matter. It can be thought of as the same if you're going to sit there and say now you're doing the experiment with a constant velocity. If you do with a constant velocity, your force times distance work rule won't work anymore because the distance will just be twice.
Or moving the road and keeping this stationary. That the force we're measuring is measuring the force.
You're just measuring the weight of the object essentially, okay, by creating some other, okay, a slightly different way of measuring the weight. So you're measuring the weight by sliding something underneath the weight and measuring how easily it slides under the weight. But you're basically measuring the weight of the object.
Force of the friction. And we wanted to see whether it increased or decreased. And it stays the same.
Alright, so it's oscillating below 1.5 here, and obviously when it goes faster it's going to oscillate above 1.4, so there seems kind of obvious that it does make a difference. It's not the same.
But do away with the wheels altogether, and then we got a rubbing resistance, and this shows the same. The friction is independent.
So he said it again, the friction is independent. No, the friction is dependent, and the fact is this experiment with a constant velocity isn't going to show it.
Of the velocity.
Because we're not seeing it, frankly. We're not seeing where the difference is. The difference is in how much wood is being torn off the wooden block.
See. The problem I've got is as I speed it up, we develop an oscillation, which makes the scale very difficult to read. You'd have to take my word for it.
Yeah, well, the last thing in the world I'd do is take your word for anything because you're just a compulsive liar and conniver. So instead of addressing any of the actual points, 9.8 meters per second, it says 9.8 meters per second. Why would I think a per second force can be counted based on feet?
Move much from that 1.5. It's a nuisance. There's a join in the belt and it causes an oscillation.
Yes, and so you can see the oscillation. Let's see how far it was. 1 to 2. 1.
You can't really see it.
Oh, okay, well.
But it does stay on that 1.5.
So the 2, well, it really doesn't stay on anything. So yes, it oscillates all the way from 1 to 2, which you could call 1.5. But regardless, it doesn't matter. The point is what does this prove? Except now you have a whole bunch of road passing under something, and it's the same amount of pressure being applied per unit of time. So you're just proving my point. You've moved a whole bunch of road. That's the same thing as moving the block a whole bunch of distance. And you're showing the same amount of work, so to speak. So you've gone a further distance on the conveyor belt. Let's say it's going twice the fast. So you use this much conveyor belt to create that pressure. And now you're using this much conveyor belt. And your pressure is the same. So you've applied the same weight over the surface, and per surface area you've obviously endured less losses to the material. So clearly the friction went way down because you didn't double how much pressure the weight was, because you're going twice as much road friction. So you have twice as much friction at the higher speed, and yet you're saying, look, it's the same pressure. Well, if it's the same, then you've basically proven my point. That you're proving Galileo's point, that the work done doing the first little bit is the same as the work done doing the 3. The 1 and the 3 are the same amount of work. So if you're going up against gravity, it's the same. You've opposed the same amount of force in the first 3/4 of your voyage that you're opposing in the last 1/4, because it's about time, which you keep ignoring. So look at the effort they go to. to contrive an experiment. So here you can clearly see it's oscillating between 1.5 and 2. So it just kind of depends on how you do the experiment, right? I mean, it's clearly over the 1/2, stays above the 1/2. So he's now, and he's going even slower. So it's now the block has gotten hot. Maybe now it's sticking more. Who knows? But clearly the number isn't exactly the same as what he started with. So this isn't exactly what you call a clinically precise experiment.
It certainly doesn't drop as we go faster, which somebody on the internet was suggesting.
Okay, that I suggested that. That's what he's suggesting. So again, just more lying. You have to lie about what I suggested. What I suggested was Galileo correctly diagnosed how gravity works 500 years ago, and that you morons, okay, are trying to debunk him somehow. All right, and you're just using all this kind of chicanery to do it. This bullshit. So even though Newton says it's a per second force, you're sitting there telling me it somehow has something to do with the movement of a conveyor belt.
As things move faster over the surface, there's less weight pushing down, causing less friction.
There's less weight pushing down, he just said. What are you talking about? Yes, per foot on the conveyor belt, there's obviously less weight. Are you contending per foot of the conveyor belt there's not less weight at the faster speed? It's kind of obvious. Less contact. I mean, there has to be less contact or this number would have gone twice as high if there was the same amount of contact per foot. So obviously there has to be less contact.
Well, that's clearly not the case.
When it clearly is the case. So again, you lose. I mean, the conveyor belt was whipping across. You're doubling the speed. Now, what you should do is measure how much voltage, how many amps watts you're putting into your conveyor belt when you double the speed. And you'll see maybe it's not 4 times as much as your theory predicts. The Jesus crap that you're trying to propagandize for says it uses 4 times the electricity. Well, why don't you show us that?
Cheers for now.
Cheers for now. I mean, another garbage experiment done badly. So again, these people all advocate that more of these bad experiments should be done. That this is good physics. All right, so we might as well do the comments while I'm here. They're close to being on the screen. I suppose I have to make something smaller. I don't even know if the video was properly centered, but who really cares? You need to see it. It's pretty generic. We already been there and did that. All right. Okay, thank you. I actually want to suggest you do it without the wheels myself, but I see you took it to do it before I asked. That's great to see. Gary has been clearly and unambiguously saying that faster velocity makes things less heavy. I never said that. Per foot on the surface, you're hitting more surface area. So again, they have to keep lying. All right, so let's just do it again, right? Because this is what they're evading, okay? Something this simple, they're evading. They won't respond to the actual argument I'm actually making. Okay, they just have to keep lying. All right. So, and it's not that complicated an argument, right? I mean, why do they have to lie about the argument? Okay, so this is what Galileo demonstrated. So it goes for going up or it goes for going down. So what the truth is, okay, is let's just say we're doing the down case. In the down case, if you drop something, it'll be going a certain velocity. So we'll just call that one velocity. And if you drop it from 4 times the height, you'll only double the velocity. Because 4 times the height is twice the time. So it's 2 units of time. So even though this is 3 units of distance, it does this 3 units of distance in the same amount of time as this. So this ends up being the same as this. Everything the same is from here to here and from here to here. And it only changes here because you're acquiring the velocity from the first and the second to fall. And so that is now going to provide you with this extra increase in your capacity to travel distance. And essentially you're traveling some of the distance for free. And it's still only 9.8. And the fact is when it hits the ground, it's only twice the weight. It only weighs twice as much. It only has an impact capacity, a capacity to be measured on a spring Okay, that is 2 times. 4 times the distance, only twice the weight. This weighs, 1 weight. This weighs 2 weights, okay, on the spring. That's the fact. For this height, this height. All right, and again, the idea is very simple. As time ticks, okay, that's how this force pushes, okay? So it's 9.8 meters for a period of time. This is only 2 seconds. This is 1 second, or one unit of time, 1 time unit. This is only 2 time units to go 4 times the distance, because obviously you're going to be going at a faster velocity. And then the same exact thing happens on the ground, okay? So if I take 2 objects and I move one twice the velocity, it will go 4 times the distance across the surface. All right, that has to be a surface, okay, because we're applying, okay, the force down, all right, creating the capacity to lose your energy to the surface. And the fact is that this giant section here, okay, will be the same weight of gravity. 9.8 will go into this section, and then 9.8 will go into this section. The same amount of force, okay, this is all you're going to get. Take off the seconds if you want for the purpose. It's 9.8 pounds. It's 9.8 anything. The amount of it is the same hitting this small amount of surface, and it's spread out, of course, over this surface. So there's only 9.8 units of energy hitting this surface, and there's 9.8 units hitting this surface, because it's about the time. All right, so this motion, just like in that case, this is exactly the same as this. And obviously this is where you're going half the speed, right? I mean, they're starting off at V2 and V1, okay, so if this is exactly the same as this is where it's starting to go just V1. This is where it loses half its velocity. Here, at 3/4 of the distance. Not at half, where you would expect if the friction was even. If you were losing the same amount of energy per foot, you'd expect the halfway point to be the half velocity point. But it's not. All right. So I've drawn this, it's got to be a dozen times at least. And I've drawn it like 4 times in the last 6 videos. And they keep doing this bullshit. Okay, so I don't argue that anything gets lighter. What I argue is that obviously if you're going across a larger surface area in a small amount of time, what I've stated is if I go across this scale quicker and quicker with an object, it will in fact weigh less. So if I let it sit, it weighs a certain amount, 10 let's say. I make it go a little faster across the scale, it weighs 9. I go a little faster, it weighs 7. I go a little faster, it's going to weigh 5. Faster, I go only 4. And eventually I can go fast enough where it won't weigh anything. And that's the truth of it. Because it's about how much time you're on the scale. Matters. Very important, actually. Gravity is a time-dependent force. It takes time for you to collect it. You have to collect it over a period of time, and the collection over time is the constant part. And all your other variables, you can change a variable, but you can't change the fact that it's going to be time-dependent. The force only comes in discrete bits over time. So again, just more lying. They can't help it. They just can't. They can't not make their argument layered in lies. All right. Gary has clearly and unambiguously saying the faster velocity make things less heavy. So he puts that in quotes. Just a lie. It's a fucking lie. Per surface, per unit of distance. Okay, and makes them have less contact with the surface. It's just a fact. They can't have very good contact if they're not on the surface very long. That's a molecular fact. Okay. Do you know what measures the friction force ? A force meter. That's what measures force. Weight. All energy is weight. It's momentum. It's a mass hitting something else with a velocity. That's energy. Sorry you haven't figured that out yet. Again, a 500-year-old idea that's stumping them. If he says otherwise, what? If I say, where did I say otherwise to what? This is saying, I said this. Do you know what measures the friction force? Question mark. A force meter. That's what measures force. If he says otherwise, yeah, I'm saying that you can just measure it with this object. So if you make a scale for any size object, you can just measure its impact, its contact weight. Contact weight is what dynamite does. It's what everything does. It throws bits of crap at a velocity, and it'll bend and move a scale, and the scale will tell you how much energy it has. He doesn't know what friction force or what friction force or the force meter is. Yeah, I have no idea what you mean by a force meter. Okay, besides it being a spring of some kind. But anyway, obviously that's the whole subject here. You don't know what 9.8 meters per second means. You don't know what per second means. You don't get the idea. And then you're really stupid because you'll say something like per second, like you need to say it twice, because I guess you're so autistic and retarded that you need everything repeated, everything twice. So everything twice, repeat. Just say every word twice because you can't understand the concept the first time I said it. Per second isn't enough for you. I have to call you asshole twice, then you'll get I'm calling you an asshole. You're an asshole. Alright, meter is, and he needs to do a little reading up on these things. So I've played all kinds of videos, on the subject. I'll play another one today if that's, but, just more horse shit. I mean, this has obviously been part of the conversation for 2 years. He hasn't been able to refute anything I actually say. Again, he has a video up where he's playing me talking about the flaws in their theory, and he has no counter argument to anything said in the video. Nothing. Do you know what else? Question mark. The force meter doesn't show that the friction force gets lower. So I don't understand. So I guess he's calling it the spring a force meter, right? So just perfectly consistent with what I've been saying. Momentum is force. Okay, as Newton would say, you want to increase the energy something has, just increase the force, the same proportional amount. Twice the force, twice the motion, twice the momentum. Force is momentum. All right, the force meter doesn't show that the force gets lower. It's clearly obvious lower per foot on the conveyor belt. The conveyor belt per foot is doing a lot less work. Okay, when he increases the speed of the conveyor belts, quite obviously doing less work. Per inch of conveyor belts doing less work, obviously. Okay, Gary has to be an absolute liar to deny these facts. So what facts were in this? I didn't see the fact part. So where was a fact? I don't know. Did you see a fact? I didn't see anything asserted as a fact. So where was the fact? Oh, I saw you lie about what I said. What did you say that means anything? I mean, this sentence against, do you know what measures a friction force? That's a statement of a fact? I don't know, that's a question. A force meter. So he didn't tell us what a force meter is. I keep arguing that scales are the man. Scales are great energy measurers. I've asserted that over and over again. He couldn't be this confused, right? Maybe he's an asshole per asshole. I mean, maybe you need to say it 3 times. Because he hasn't figured out that I'm the one saying scales measure energy. I don't know. This is just so pathetic. Okay, when a wheel rolls across a smooth surface, so the John Walker guy can't stay on the subject, right? We're not doing wheels now. The wheels of the indoor bicycle runners, for example, the friction between the wheel and the track can be extremely small, and in theory can be 0. Yeah, well, obviously, most exercise bicycles work by creating tension in the wheel. That is, they use a fan blade or something, so you have to do work to go faster. So it creates more friction. I mean, I have a couple exercise bikes. Yes, one of them just applies pressure to the wheel. The other one has a belt around the wheel. There's all kinds of. One of them has a chain. All right. When a slick object slides over a smooth surface, like you have with curling, for example, the friction between the object and ground can become very close to zero. Yeah, but yeah, again, frankly, this isn't what this subject is about. Now, obviously, if he could make that conveyor belt go really, really fast, every time he hits that tiny seam, he would end up really radically reducing. First, there's a bang, and then the momentum friction. That's when the spring relaxes and says, this is easy. Because he's basically lifted the object off the fucking surface. But whatever. And we know that curling depends on creating the liquid surface and blah, 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 blah. And it's really floating on water. In small experiments like kinetic energy of object wind, the kinetic energy of the object winds down in a straight line linearly. So what does this even mean? So he's saying in small experiments his kinetic energy theory is broken. That somehow doesn't go 4 times the distance. But he's saying it because there's no friction. So again, look, the argument isn't that complicated. I mean, clearly there's a gigantic difference between, I launch things off a surface, right? So one of them's going twice as fast. And so the only thing collecting the energy, the only thing resisting the motion is air. And the air resistance is so minimal that, yes, the twice as fast thing will go twice the distance of the half as fast thing. And, if you do their math, it doesn't work. Because, there's no kinetic energy advantage being shown because you're not collecting the total energy. Now, if I collected it as weight, I'm still going to have the same problem because I'm just going to have weight in 2 directions. I'm going to have the weight of gravity, you drop the object, it gained a velocity, and now it hits the surface in this direction with a certain weight. And the weight this way is still going to be the same too because you didn't lose any velocity. All you're going to have is twice the velocity, twice the weight. You're not going to have 4 times. All right. When a water skier goes too slow, a water skater? Skier. Yeah. Anyway, they will stick. Therefore, the speed gives a larger force. Higher speed is more surface per unit of time. Yeah, exactly. And he just showed that even though it's more surface and presumably more work being done, there was no indication of that in the sense that the friction wasn't applying that. It was applying less proportional to the speed because it stayed constant. For it to stay constant, it would have to be applying less per unit of conveyor belt moving. So clearly a huge non-equality. All right. Not sure you are disagreeing with DS. Yes, well, at least MC's a little bit more honest. If they did experience the same friction over the same time, then the 2x velocity wouldn't go 4 times the distance. So he's at least done the tiny bit of figuring it takes to figure out that, yes, if you were pulling the energy out of it at the same rate, that you couldn't go 4 times the distance if the same amount of friction was happening per foot. If the 2x velocity experienced twice the friction, it would stop at the same distance as the 1x velocity. So, the point is made. They say it would have to be 4x the friction, but whatever. Because obviously they're saying it's for 4 times the energy. That's their theory, right? So instead, like I said, they could just put one of those, I don't know what they're called, energy efficient, those devices where you just measure how much electricity something's using. And so when he doubles the speed of the conveyor belt, he could just see if it's 4 times as much electricity to do that. That would be an experiment to do. I mean, obviously it doesn't prove everything, but all kinds of different inefficiencies can be built into machines. But I'm saying as a general rule, I don't think any of those experiments are going to come out to their liking. I don't think if I do it with a light bulb, 50 watt versus 100 watt, I'm not going to find that I use 4 times the energy to light the 100 watt light bulb. So I should get one of those. Yeah, so somebody should do those experiments, right? They're not that much work. But they probably should do it with a really good device, some sort of oscilloscopy thing or something, to get a really accurate measurement. And just find out that we can't find on the surface of Earth a single electrical motor or electrical device that follows the kinetic energy rules, where if I, get twice as much horsepower or wattage out of it, that I have to use 4 times the energy input. Then we'll find that none of that's true. Yeah, that never comes out that way, ever. Just like if we actually did the 4 times the fuel argument for a car or anything else. It'll never be true that it takes 4 times the fuel to go twice as fast, because it doesn't. Because it's all wrong. Alright, so is there anything else I need to say? So, I guess just to point out, just to make sure we understand the difference between his experiment and what I have illustrated, and the experiments are frankly relevant to other experiments done, like the Brozo billiard balls experiment and different other ones that actually have been done, that don't... that frankly, well, they're all bad. They all could be done better. Nobody good is doing the experiments. No fair person. All right. So again, the simple experiment was you want to test for its energy. If I just throw it off a table, okay, at twice the velocity, I can't measure its energy unless I measure how heavy it is in this direction and how heavy it is in this direction. So I have to measure. This one was irrelevant, but it is going to be real energy. It is going to impact the ground with the gravitational energy added to it. So it's going to have more than just as twice the velocity, because it's also added gravity, but it's not going to be 4 times. But anyway, we know that if this one's going twice the velocity, it's only going to land twice as far. Okay, so it's going to be just two units of distance. 1, 2. All right, so we know that's true. All right, so that's well established. All the physicists say so. Okay, I shouldn't have to argue it, because every single physicist says yes, this will be the outcome. This one will go 1 unit of distance in time, and this will go 2 units of distance in time because of the velocity, and there's not enough air resistance to stop them. So unless I shape them to be affected by air resistance, I can't change this outcome. All right, and so, but we're not measuring its energy because we're not taking its energy. So the idea of rolling something, at least now you have a way to measure its energy. So let's understand his conveyor belt is a constant velocity. So that's like saying I'm going to take this and I'm going to make this one go twice the velocity, but it's going to be a constant twice the velocity. It's never going to slow down. So I'm not going to extract the energy from it. I'm just going to keep pushing it against the friction and maintain it at a 2 times the velocity. Experiment. Well, we know then the outcome is this is going to change. This isn't going to be 1/4 anymore, and this is going to be a whole. No, we know that this will go half now. So we know if I force it to be a constant velocity, this is going to go 2 units of distance, but it has 2 units of velocity. And that won't change. So clearly his conveyor belt is not measuring the same thing, because he's not he's not using friction to extract the momentum from the conveyor belt or from the object. So he's not measuring anything called its energy. Okay, he's just measuring how much, again, he's basically just measuring how much does the object weigh. Okay, he's measuring the gravitational force. He's not measuring how much work friction is doing, because he's not measuring how hot the conveyor belt is. He's not measuring how per foot, how much work the conveyor belt is doing. Because obviously if you do the rolling thing, again, the point will be is that you're going to end up with this 3-to-1 relationship, okay, where you're going to do the same work in this space, that is the same extraction, as you do in this space. There'll be exactly the same amount of hits to the surface. Dents, however you want to measure it in. Dents, ticks, little white spots, little pieces of paint. Same paint on this surface, they'll end up on this surface. Alright. So clearly not a linear or even distribution of paint. Alright. So clearly not the same experiment. Not very useful in terms of showing us that there's 4 times the energy in something going twice as fast. Alright. So that's it for the comments. So one honest one. Close to it anyway. Better than the usual crap. Alright, so I guess we can see if there's any comments, but I'll just probably play an interesting video. Okay. Alright, so we'll go back to this and we'll play this video. And should be able to make that. Boy, what the hell is wrong there? It's in the wrong window, that's what's wrong, I guess. No, it's the right window. Why is it that weird size? Oh, that's better. I fixed it all on my own. Alright, so this is a guy who made videos 10 years ago called Physics Michael, which probably isn't a great name. But whatever. Not very catchy. Let's reload it just to see if his view numbers are a little better than the pathetic numbers. 18 views. I mean, that's just, 24 hours. So, I mean, it's just kind of tragic how broken the internet was. So, 10 years ago, he used to get, a few thousand views anyway. But really pathetic. He has 9,000 subscribers. Obviously, they're all dead now, I guess. They all graduated high school. And have moved on in their life, I guess. So anyway, just pretty tragic. This is how the internet works. So this subject is not directly related. So obviously, there's a pile of it that's relevant. So yeah, the audio isn't too good. You can't really tell what he's talking about because he doesn't relate his equations to the statements he's making. But they're just general statements, so I just figured it's worth something as just somebody articulating these general statements.
Gears one more time, just a little bit. I want to finish this off by talking a little bit about energy and angular momentum, 2 kind of quick quantities that we're going to be seeing come up a bunch of other times throughout the course. This concept of energy, energy is a mathematical property of different kinds of systems. So it's really just a number.
So again, to say it's a mathematical property is, it's just kind of, to me, just cheap shit talking. We're just formalizing observations. It's a thing observed in the universe. I mean, it is an event that takes place in the universe, this thing called energy. It's a happening. All the energy things are events, okay? And the event is basically made out of something hitting something else. And sometimes the thing can be really small, it can be going insanely fast and it hits it, or it can be a big thing and it can be going really slow and it hits it. But it's just stuff contacting other stuff and they're exchanging their condition. That's energy. In my opinion, that should be the real definition of energy.
But this number is something that if you have a way of calculating that energy, that total amount of energy won't change.
Okay, so the obvious point I would make is that if the universe did start off with big pieces moving slow and it was, through contact converted into small objects moving fast, and you conserve the momentum, you wouldn't conserve the energy. You would end up with an energy, more energy in the universe. And then likewise, if you want the opposite, if the universe was slowly turning little things into big things, little things moving fast into big things moving slow, it would be losing a ton of energy. So obviously I would be using the word momentum here, not the word energy. You conserve momentum.
Energy can't be created or destroyed.
Yeah, momentum can't be created or destroyed. Should be the argument. You have to conserve the motion and the mass. So the quantity of motion, as Newton put it. I mean, they talked about it like it's a quantity of motion. There's a quantity of motion in the universe. You have to maintain the quantity of motion. And it's just going to be distributed over big things or little things. And it doesn't matter whether it's big things or little things. You're going to conserve the momentum. The masses times the velocities will always be the same.
So if I have a system and I know how much energy it starts with and then it goes through some weird transition, I know it's going to have that same total amount of energy.
So again, he doesn't define what he means by energy. So he really does believe in 1/2 mv squared. So, you know, like I said, there's lots of implications to that statement where I can just point out how you're violating your own rule, okay? Because you are going to create and destroy energy anytime you have an event in the universe where you distribute the energy to lighter things. You'll end up with more kinetic energy.
That I had before, because energy can't be created or destroyed. If something's going on and some energy leaves that system, I should be able to know exactly how much energy left and how much energy is remaining, because
well, you could guess at it, but the fact is the law is established based on the stuff we can see, and then we just use our brains to model the parts we can't see. So we're not going to be able to see the subatomic particles doing all of their actions. But we know it takes place, and we know we can model it, and that it is consistent. So there's no reason to doubt that the same rules apply in terms of conservation rules. But we don't get to actually see it.
again, overall, throughout the universe, energy can't be created or destroyed. But it can change between many, many different forms.
So this is another one of these places where I just say this shouldn't be emphasized. The energy is really just motion. So it can be changed in the sense that you can give momentum to a small object or you can give momentum to a big object. And the amount of momentum you give it will change, obviously, based on the proportionality of the mass. So the small mass will convert the energy into a larger velocity. A large mass will convert the energy into a lower velocity. And that's pretty obvious, but it's just masses moving velocities. And so he's missing a giant part of the story about masses moving velocities because underlying it, he doesn't believe in that. He believes that somehow velocity is twice as important as the mass. Not even twice, right? I don't even know how it's exponentially more important. I mean, that's really bizarre, frankly.
So the total energy content of the universe is constant, but again, there's many, many different kinds of energy. In fact, let's talk about some of those different kinds of energy. Take a moment and try to pause the video and think of how many different kinds of energy can you...
All right, so what I would have said is, pause the video and imagine the universe as made out of all these constituent parts and figure out where something besides an element of mass has to move a velocity for something to happen. And it's always just an element of mass moving a velocity. And obviously when they say photons don't have a mass, they just made that up. I mean, they clearly do have momentum. So clearly they do have a mass. It's just a very infinitesimally small minus 10 to the minus 32 mass, but it's a mass. And when they hit something at their speed of light, it equals an impact wattage. There's a weight. They have a weight when you move one at the speed of light.
You think of. So pause the video. How many types of energy can you think of? Okay. So hopefully you did that. Let's go over some types of energy. There's kinetic energy, the energy of motion. So If I have an object, the faster it's moving.
So it's bizarre again. So this word kinetic is being used for two different things: kinetic versus potential, and then kinetic in terms of kinetic versus momentum. And so it really makes this argument even more difficult, because obviously I'm not disagreeing that energy is motion. I am disagreeing that it's, squares with a velocity.
The more kinetic energy it has. We've got this thing called gravitational potential energy. If I take
he's an astronomer apparently as his profession and all that kind of crap, and it just seems weird to me that they think of it in these terms of gravitational potential energy, when I think it's just kind of obvious that whatever it is, it's a stream of energy. It can only be modeled as a stream. I mean, when Leonard Susskind teaches relativity, he teaches it as a stream of fluid, because it makes sense to. It works. So mock gravity is the way you teach it. So you're tapping an energy source. So you're just sticking something in the momentum waters.
An object and I hold it higher up in a gravitational field.
So this is the weird part, right? We know as you're holding it higher, you're actually in technically less gravity. So you're reducing the amount of the flow of the river. Okay, the current is a little tiny bit less up there. And all you're really talking about is the longer I let it fall, the more of the stream's energy it's going to collect. And it's going to keep collecting it in units, okay, of as if it's getting hit by BBs or some energy source that had an infinite speed. So now, even though the speed of light isn't infinite, it's obviously much faster than these objects are falling, so it's close enough. And what you're basically just saying is you're throwing little bits at it, and with each bit, you're going to increase its velocity. So the longer you let it fall, the more little bits of paint are going to hit it, the more little bits of BBs are going to push it. So it's going to keep going faster and faster and faster until it reaches the speed of the stream, which is the speed of light. So you have a very fast stream of little very tiny particles, and you're just saying, how often am I getting hit by those particles? And you're getting hit at a rate of 9.8 meters per second at that location. So in 1 second you would expect you'll have a certain velocity, because you will be hit by a certain number of these little bits of stream water. A very fast stream.
It has more gravitational energy.
So it's just kind of silly to say it has more energy. If I move the ground up higher, it loses all of its energy. So, all I have to do is move the ground up, and all of a sudden it doesn't have any energy anymore. It's about how long it's going to be allowed to fall in the gravity. You've already added up how long it's going to fall. The distance is just saying, how long am I going to let it stay in the stream without sticking a rope across the stream to stop it, before putting something in the way to absorb the energy it's collecting. So that's all you're really measuring, is how long you're going to allow it to stay in the stream. There's not more potential up here. The potential is just in the fact that, yes, as long as the ground stays down there, you have time to acquire a faster and faster velocity, because you're going to allow it to get hit without it hitting something else, without it banging into any rocks in the stream. So it's going to go faster and faster and faster.
If I let that object fall towards the Earth, well, it loses that gravitational energy. Well, let's look at this specifically. I lift this up in the air.
Let's understand. It doesn't lose anything. Of course, it's gaining with every little tiny inch it falls, in terms of inches as time increments. Okay, I should avoid distance at all costs. But whatever unit of time, it's getting hit, and it's getting hit, and it's getting hit. So it's gaining more and more energy. And then when it hits your hand, it's going to show you that I did this collecting of force, because now I'm going to weigh different. Because now I have a higher velocity, and my velocity gets multiplied times my mass to figure out how much I weigh.
I'm giving it gravitational energy. Let me reset my camera. So I'm lifting this up in the air, I'm giving it gravitational energy. And when I release it, that object starts to fall. And as it moves downwards in this gravitational field, it loses some of its gravitational energy.
So again, it's just silly to say it loses energy. It starts to run out of room to keep falling. So yeah, there's less future in front of it. Okay, it's collected energy. So when it's at the halfway point, it's collected half the energy it's going to collect because of the period of time it's going to be in the gravity. So we know that's not even true, right? It's not halfway. It has to get all the way down to 3/4 before it's going twice its velocity. I mean, the velocity it will collect. The first quarter, it collects half the velocity. Just in the first quarter of distance, it falls. So the first quarter, it's already achieved half the final velocity down here. So I mean, those are the important facts that you have to recognize. This is time dependent. That you're only going to collect the force in units of time.
Does that energy just get eliminated from the universe? And if not, where does that energy go? Think about that for a second.
So we know it's not a unit of distance of energy, it's a unit of time. So it fell a certain unit of time at 9.8 meters per second. It collected energy. So the only energy it has is how much time did it collect 9.8. That's it. The distance isn't meaningful.
So we start with gravitational energy when it's up here. I release the object and it falls downwards. As it falls, it's losing gravitational energy, but notice it's moving faster and faster. It's gaining kinetic energy.
So I mean, it's just kind of a silly thing to say. It's obviously collected energy from the gravity. That's simple. And the amount of time it was in the gravity decides how much it collected. You could just, again, the bucket and the rain analogy just works fine. It's a bucket. The mass tells you how big the bucket is, and all you're going to do is collect the rain falling. And it doesn't matter. This motion is irrelevant because the raindrops are moving the speed of light. Again, so your differential to the speed of the force is so huge that, the little tiny bits of difference, like you're going a little bit faster, which means fewer raindrops get in your bucket. Well, at the speed of light, you're not going to see that. Just as I can't see it happen to my hand. My hand doesn't reflect less light as I move it in these incredibly slow speeds. The actual fact is it did reflect less light when I moved it away from you, but it's so tiny because I can't make a motion that's nearly fast enough to see that difference. But the fact is you just clearly just collected energy based on how much mass you had for the energy to stick to.
So in this system, when I drop this object, well, it loses that gravitational energy, but it's not eliminated from the universe. It's being converted to kinetic energy. When it hits my...
So it's not converted, okay? It's energy in the universe. It's collected by the object. It's all just mass and momentum. You could argue you got hit by photons that had the potential to move you. Those invisible photons, whatever you want to call them, those discrete quantas of energy that make up the gravity have been collected by the object and are now possessed by it.
And... well, you can hear a little thud. There's some sound energy that comes out of that. There's some vibrational energy that goes into my arm. So, again, energy isn't being created or destroyed. It's
well, it is by your theory, because you're saying it only weighs twice as much when it hits the ground. So it traveled 4 times the distance, but it only weighs twice as much. And you're saying, okay, that somehow, okay, that has 4 times the energy. So it has 4 times the energy, but it only weighs twice as much. I mean, how can that be reasonable? How's that a reasonable statement? I'd say it's pretty unreasonable. And it gets more and more unreasonable the faster and faster you let the thing go. Quadruple the speed and zazuple the speed, and you get even crazier disproportions. The weight won't match, won't be anything close to what you claim its energy to be.
It's changing between lots of different types. Other types of
So
energy.
all there is sizes. So I would argue the only thing there is different sizes of energy. There's not different types of energy. The energy is always just mass and velocity. And there's no other type than a mass and a velocity. So it's just really big things, elephants and hoobies. However you want to. It's just little tiny things moving, really big things moving. That's all there is.
That we're going to be talking about in this course. Thermal energy. If you take your hands and rub them together, I'm trying to move my hands very quickly, and friction causes them to slow down.
So friction, whatever the magical word, contact. Contact means you're going to exchange motion between one hand and the other hand. So you're just going to keep putting motion back and forth between the two hands because you can't destroy the motion. So you're creating a whole bunch of motion and you're confining where the motion can go. And so it's getting hotter and hotter because you're basically just shooting the motion back and forth. It's reflecting a lot.
Down. So it's removing.
And so he's not really talking. He's not going to talk about the fact that what you're really doing is moving and scraping and breaking a bunch of atomic bonds. And each time you do that, you release a little bit of chemical heat energy. Some of these little bits that are holding it together. So you're making a bunch of you're making two big objects moving into a bunch of little tiny objects moving. That's the way it should be understood, is that I have big objects and I can move them. And they're not in contact with each other, so that's all they're doing. They're just big objects moving, and I can move a little bit of the atmosphere, and that's it. Nothing else to see here. But when I put them in contact with each other, what I'm going to do is convert these big things into a bunch of little tiny bits of sawdust, hand dust. I'm going to break a bunch of little pieces off and give them velocities. And that's going to be felt as heat.
Kinetic energy, and it turns that into thermal energy. It increases the kinetic energy of the atoms in your hands. There's chemical energy, the energy stored in chemical bonds. So, for example, how did I get the energy to...
So that what I would just analogize is that you could, I could draw an atom and I could have an electron here and an electron here and an electron out here and an electron over here. And I can have the nucleus in the center that's positive, net positive. And you could just make a simple argument that the pressure between the electrons and the pressure attracting them to the protons have been balanced. And if I do something to disrupt that balance, I pull out one of the electrons or somehow I turn the nucleus so it isn't, the electrons can no longer see the protons that they were attracted to, so they can't see them anymore, then the electrons are going to be propelling each other and they're going to push on each other with a pressure that's going to push them out. So all the atomic bond kind of stuff just really has to do with atoms contracting and expanding. And those two motions eat energy and produce energy. Push out into the universe or consume some, elastically consume some of the energy in the universe. They reduce reflections or increase reflections. And that's what's really happening.
Lift this object up in the air. Well, I had lunch, and my lunch is made up of materials that have, various chemicals that my body can break down. And when those chemical bonds are broken and reformed in different ways, they can release different kinds of energy. And that powers my muscles and allows me to lift this up in the air. So
it's not really saying much, right? It powers my muscles. What your muscles will do is create ions, and contract and expand based on creating electricity that has the effect on the muscular surfaces of creating a bunch of ions that go across the surface. So you're moving a bunch of electrons in the process of creating the contractions and expansions of muscles. So it's, not a great analogy, and what you really should talk about is leverage. That is, his skeleton structure is using leverage and the contraction principle. So there's a huge correlation between, the atoms doing the expanding and contracting thing in terms of how they're being affected by their chemical energy, and the fact that the muscles are doing the same thing. They're contracting or expanding, and then you're using leverage to convert that expansion and contraction into a specific amount of movement.
One thing that we're going to be talking about when we talk about the properties of stars is mass energy. This equation that I'm guessing most of you have at least heard of before.
Yeah, that stupid E equals mc squared. Just sort of, it's just such an outrageously bizarre number that no one's ever going to test it in any kind of real way. It's only just going to be relative comparisons, and I would argue that there's nothing intrinsically energetic about a piece of mass. It's almost that mass is almost it takes up space in the universe. And space in the universe is energy. So if you thought of the universe as just being full of a bunch of little bits flying in all directions, you could understand that any box, any drawing I make of a hunk of space would have a certain amount of energy in it. And mass takes up space. So mass is basically reflecting or occupying that piece of space. By occupying the space, it's creating more pressure in the universe. So if I did have a box with BBs in it, and there was only a certain number of BBs, and they bounced around at a certain rate, and there was a certain number per square inch, I could guarantee that I can increase the rate of the energy of the BBs if I just stick a block of matter in there that reflects BBs. So the more blocks of matter I put in to reflect BBs, the less free space they have to move in, the faster they'd end up moving. The more energetic they would be, the more per empty space there would be.
Or E equals mc squared is that mass, in certain conditions, can be converted into a huge amount of energy. So this is the energy in a certain amount of mass, and this C value, that is the speed of light. Speed of light's a big number. When you square a big number, you get a freaking huge number.
Right, it's freaking huge, and it just seems a little preposterous that if I was to just take an electron, for example, by itself in the universe, it really can't do anything. It doesn't have any innate energy. It's just going to occupy a certain amount of space, and it'll have a certain amount of energy because it's occupying a certain amount of space. But it's not going to be mass times the speed of light squared amount of energy. And it really does take the whole event of charge, where you end up creating disproportional pressures between things, attraction and repulsion, that you have the capacity to store a bunch of energy in atomic nucleuses and in atoms. That's where you're really doing the mc squared thing. You have to have, the elemental universe is not mc squared.
So even a small amount of mass, if that's converted to energy, you can have a huge amount of energy output out of that. And this is what's going on in the fusion reactions inside the sun. There's probably other kinds of energy that you might have thought of, things like electrical energy, wind energy, geothermal energy. One that we're going to be talking about.
So none of these are these are all just saying, you're just saying fluids are moving. Okay, so wind is just a fluid moving. You could argue, the tidal energy is just another fluid moving. Okay, the mass and its velocity. So these are all just ways of tapping. Hydroelectric is it's just another fluid moving. So not it shouldn't be implied that these are discretely or fundamentally different. They're just atoms moving. And you can have a big clump of atoms moving, or you can have a small clump of atoms moving.
In a couple of classes is light energy. So when sunlight comes in and hits you, it starts to warm up.
So this is the part where they really break physics, because they don't think that energy is related to a mass moving a velocity. So they, I mean, they say it has zero rest mass. A photon never rests, so the whole idea is, you're almost saying, why are you even talking this kind of gibberish? Show me the resting photon, okay? They don't rest. They're doing the Descartes thing. They're always, the motion is somewhere. You just find out where it went, but it always went somewhere. Never stops.
Your body, well, that thermal energy had to come from somewhere, and it's actually stored in the light itself. So again, in all of these cases, we can have situation where energy changes between some of these different types, but again, the total energy content of
So he should just say different sizes, and as soon as he says different sizes, then he has to concede that, well, the total can't be conserved if I make more small things in the universe than there was before. So if I just break one big thing, then I have converted, I have created free energy in the universe, and unless something else undoes it, at this moment the universe has more energy in it because I broke a big thing into smaller things. It's just a fact.
the universe is constant. So let's see how this comes into play with talking about these orbits.
Momentum in the universe is constant.
I said when I hold this object higher up in the air, it's got more gravitational energy.
Which is stupid. So again, and orbits are made out of something with a pre-existing velocity. So the thing that needs to be understood is that the orbit is just controlling something that's already has a velocity. So the object has its own momentum in space. And all you're changing is the direction of its momentum with the gravitational force. The gravitational force isn't giving it momentum. It doesn't have momentum because of the gravity. It has momentum because it has a velocity to start with. If you don't give it any momentum of its own, it'll just fall right into the earth. So obviously its momentum against that direction, perpendicular to it, technically, that is the reason why something can get into an orbit. It can't get into an orbit if you don't give it a pre-existing velocity.
More gravitational potential energy. In the same way, if I have a star and a planet, and that planet's really far away, it's high up above that star.
So again, it's going to imply there's more energy higher up, when no, there's just more opportunity to be affected by the force. There's a longer amount of time you can be affected by it. So it's really happening to an object when it's going through this ellipse. That is, it's going to speed up here and then slow down and then speed up and then slow down. And what's obviously happening is one side of the orbit, it's moving away from the object, and the other side of the orbit, it's moving towards the object. When it's moving away from the object, it's doing work against the gravitational force. That's why it's slowing down, obviously. And then when it starts to move towards the object again, the fact is that the as it turns that curve, it's going to be moving towards it, and so now it's going to be gaining speed from the increased velocity. And it always turns out that these ellipses, have a rule to them, okay, that your velocity will increase proportional to your radius. So it's just like a lever in a sense.
Then it's got a lot of gravitational potential energy. As the planet approaches the star, if it's got this...
So most of these ellipses are not nearly as ellipsy as this, right? So the Earth only has like an 8-degree ellipse or something. It's very slightly off the center. It's not hugely off the center. And the reason why things are in ellipses, in my opinion, is just because everything, you have to do exactly the right velocity, has to match the object when it goes into the gravitational well. And if they don't match exactly, then there's always going to be an ellipse. So it's like you're getting bombarded by the universe constantly, and the universe would have to bombard you in just the perfect velocity for you to fall into something like a perfectly circular orbit. It has to hit you at just the right time to slow you down just the right amount to allow you to stay in an orbit or speed you up.
Kind of higher eccentricity orbit, then when the planet gets closer to the star, it's losing some of that gravitational energy. Where is that gravitational energy going? Well,
so he's saying it's losing potential energy as it's getting closer to the sun. And of course it's not. It's gaining more and more energy. It's getting hit by a greater... It was 9.8 meters per second here. It's only 2.4 meters per second here. I mean, it's obviously increasing how much energy it's gaining.
ends up ending up in this planet as more kinetic energy. It's moving faster and faster. So as the planet kind of, in a sense, falls towards the star, it's moving faster and faster, and that is going to be at its fastest at the perihelion.
So it's just gaining, it has its own velocity, and it's just gaining a velocity that's in the same plane. So the gravity is adding a force, okay, and this is the way its velocity is. Gravity's adding a little bit this way, so it's bending it just a hair, and it's bending it a little more, and it's bending it a little more. And in the case of coming towards it, that bending is in the same direction, and when it's going the opposite way, the velocity is going this way, and the force is doing the opposite thing, so it's stealing the absolute velocity. It's taking away from its intended velocity, its directional velocity.
Position, it's going to fling around, and then now it's starting to go away from the star. As it moves away from the star, it's losing that kinetic energy because that kinetic energy is being converted back into gravitational energy.
So it's not obviously being converted into gravitational energy. It's just losing energy because, frankly, it's fighting a gravitational force. The force is stealing, like friction. It's stealing its momentum
by the time the planet is on this side of the orbit. So again, there's lots of different cases that you can think of for conservation of energy. It's one of the cornerstones of our understanding of physics.
All right, and I'd argue that the cornerstone is not, it's mal-shaped, okay? You have whittled it into a monstrosity by ignoring the elemental kind of square box rules. You've undone the basic principle, which is all there is mass moving that forms all energy, and contact is necessary. A mass moving that doesn't hit anything doesn't do anything. One that hits something changes things.
Those are a bunch of examples of energy conservation. Let me just give like one last that kind of relates.
Changes through exchange. It just exchanges properties. The two things hit each other and they exchange properties.
To this, when the planet swings by the star and is now on its way towards the aphelion position, that's kind of like if I gave this object some kinetic energy. If I give it some kinetic energy, it can use that kinetic energy to go higher in this gravitational field. It loses that kinetic energy, but it gains gravitational energy.
So it obviously doesn't gain anything, okay? It just loses. So there's no gaining of anything. It's just, as a practical matter relative to the sun, it's losing velocity, period. Has the same mass, it's losing velocity, therefore it's losing energy to the fact that it had to overcome a gravitational force, and the same thing will happen in the opposite direction. It'll get the energy back again, the momentum. And that's it. So yeah, it's not that complicated. There's a force, gravity, you can throw something into it, okay, it'll lose all of its energy, stop having any momentum at all, and then it'll gain momentum again as it falls, as it recollects the force. As it's going opposing the force, it's all the stuff's being knocked off of it. It's losing everything it acquired. The paint is being knocked off by the second piece of paint hitting it. You could argue it's like a sand blaster, and it's just blasting the sand you collect on the way down. So in one direction the stuff sticks, in the other direction it knocks pieces off.
Eventually it reaches its peak, can't lose any more kinetic energy, starts to come back down, and now we're back to the converting gravitational energy to the kinetic energy of the system.
Right, and you do it at a per second rate.
One last one that I want to look at is this concept of angular momentum. We're not going to worry about this equation, but
but it's really simple, okay? It's really just mass and velocity now, again, and all you're really doing is with the same thing with the lever. You're just adding a condition and saying that if it's twice the distance, then it's going to be twice the velocity. So you're just adding something to tell you that as you increase the radius, okay, you're really going to affect, okay, the velocity. But it's completely proportional.
I have an object that's spinning, that spinning object has a certain amount of what's called angular momentum. And the amount of angular momentum depends on the mass of the object, depends on what's the radius of the circle that that object's moving in, and how fast that object is moving. And
so the angular momentum is always the same. Just like other momentums, you have to excrete it. You have to extract it through some sort of friction. So if you don't use friction to extract it, it's still in the system. And all you're really saying with this experiment, this is the skater argument. You have a mass on the outside. It's going much faster. Even though it looks like it's going slow, it's going much faster. It's traveling more distance in the same amount of time. So it's going really fast. So even though the skater looks like she's going slow when her arm or leg are out, she's really going very fast. Those pieces of her are moving much faster. And when she pulls them in, even though her existing weight will spin faster, meaning it has more momentum, the fact is the stuff she brought in is going a lot slower. Okay, its velocity went way down. And so that's the difference. She increased the velocity of her core, but she decreased the velocity of her appendages by much more, okay, by a much higher factor, much more distance, 5 times the distance, 5 times the velocity. So she reduced the speed of her hand 5 times, and she increased the core by 3, let's say. And it all adds up to, yes, she's going to rotate much faster. Appearance-wise, the core is going to rotate faster.
In a lot of the systems that we're going to be looking at, this angular momentum is conserved. But this leads, if this whole thing is constant, for a circular orbit, the mass is always staying the same. The radius, if it's a circular orbit, it's always at the same radius. So if all of this multiplies out to a constant, we're going to be having the same velocity the entire time as well. But on the other hand, what if
So there's no point in saying we're all going to have the same velocity, right? Because every piece of matter in the object will be moving at a different speed depending on how far it is from the gravitational center of the object, or the weight center. So, that's just wrong to say it's all moving the same speed, because it isn't. It all has the same momentum. It doesn't. Each piece has a different amount of momentum. Each atom has a different amount of momentum.
Have an elliptical orbit?
Each atom in a different radial distance from the center will have a different momentum.
Well, if this whole quantity is conserved, if this is always going to equal the same thing, the mass times the radius times the velocity, when the radius is very, very large, that means I'm going to have a small velocity. When the radius is much smaller...
So again, that's exactly backwards, frankly. Right? When the radius is large, the velocity will be large. When the radius is small, the velocity will be small.
If this all multiplies out to the same value, the velocity has to be much, much higher in that case.
There you go.
This is the source of Kepler's second law. That whole sweeping out equal areas in equal time.
So if you took a pie from the sun and made little pies out of time, you would find that time, okay, the amount of stuff in that section will be the same volume of stuff. Okay, so distance, no, that's distance, not time. Sorry. So the distance at the fast speed you do, at the fast velocity, well, whatever. They're pi sections based on time. I think it's time, actually. Yeah, time. Time, you get a lot of distance out of a small amount of time here. So in the same time, you have a whole bunch of these little dotty things. In the same time over here, you just have a few little dotty things. So you can sort of understand that the volume, the angles, will create the same amount of area in that triangle, if you could draw it as a triangle.
That is a direct result of this angular momentum concept. This is kind of the foundational concept that results in Kepler's second.
So the real underlying principle is that it's a time-dependent force. That's the real thing that's deciding it, and that's controlling it, is the fact that it's about how much time are you affected by how much force. So it's a rate of force, it's a rate of rain falling, and then you have your bucket, and you're just saying how much time am I in that rate. If I change the rate, I'll change how much is in the bucket. If I change how much time the bucket's sitting in the rain, I'll change how much rain's in the bucket. That should be the way it's taught.
Law. So let's actually try to simulate this rather quickly. I didn't think I was going to do this, but let's give this a try. I'm going to try to simulate this kind of whole conservation of angular momentum.
Okay, so he doesn't really get to it. He pauses, does this, does that. So we'll just get to the part where he does it. Somewhere in here.
What happens when we take all these ideas and put them together?
So this is not exactly putting them together and not exactly explaining it right either, because it's optically fooling you. I mean, the slow movement, what we perceive as slow motion, is really fast motion for the things he's going to stick out. So it's going to look like they're going slower, when no, they're going to be going much faster.
Okay, the room's no longer spinning for me. So let's take these ideas of conservation of energy and conservation of angular momentum, and see if we can put them together. Okay, the room's no longer spinning for me.
I don't know what that means.
So let's take these ideas of...
I guess he did it here. Okay, he's putting them away.
My chair and try to spin myself around, starting with these held out, and then I'm going to pull my arms in, and we're going to see what happens. Hopefully I can do this without falling over, so I'm spinning around.
Okay, so that looks like a low energy state, but the fact is these things are moving with a very high velocity. Okay, so the mass in these weights is now going at a very fast speed.
Pull in 3, 2, 1.
Per foot speed. Their velocity is high. And he pulls it in, and it looks like he's going faster. Okay, yeah, his core is spinning faster, but these things now are going a lot slower. So their rotational speed, the covered distance, the amount of distance they're moving in a unit of time, has gone way down.
Okay, how long can I hold that on? A moment, please. Gravity starts to pull all that material inwards. Okay? So we're going to start imagining this. Let's say I've got this giant cloud of dust and gas in space that, just due to random motions, might be slowly rotating. At the beginning, all this stuff is really, really spread out, so it's got a lot of gravitational energy. Okay? So when gravity starts to cause this thing to collapse, a couple of things are going to be happening. First, it started with this...
So what's going to happen is, obviously this is the low energy state. The expansion is the low energy state. And you're going to gain a lot of momentum towards the center as things get pushed into the center. So they're going to start collecting the rain. They're going to get wetter and wetter and wetter. And by the time they get to that center, then they're going to be imposing a whole bunch of wetness on the center, a bunch of momentum. It's going to be now inside that core, whatever that thing you're pushing it into. So the Earth has an insane amount of pressure on the inside because of all the hits from the outside. And all that pressure, if something breaks, something fractures, something happens that allows that energy to start being released, that is the pressure to find some way to escape, it's going to escape with an intense amount of momentum. Because it's the momentum, all the collected momentums, all the action that went into that center are stuck in there.
very, very slow rotation. And as gravity pulls that material inwards, that material is going to start rotating faster and faster. So as the material gets...
So let's understand, it's the core is going to rotate faster and faster. All the other stuff has lost its momentum in those directions, and has its momentum in the direction of the core. So that's its motion. So there's a huge amount of pressure that has to create that circumstance. But it's not going faster net. It's going slower, or it's going the same speed net, okay? You have to conserve the energy.
Pulled in, it's going to be spinning faster and faster.
The core is going faster, the outside matter is going slower.
Also are saying we're starting with lots of gravitational energy, and as that material gets pulled in, well, that gravitational energy...
It doesn't pull in, it gets pushed in. That's indicating why the pressure increases as you go deeper and deeper inside, is because there's more and more stuff pushing, okay? The whole pulling thing is just... I mean, it's a place where you start, right? I mean, I'm just saying that this is what breaks your foundation, okay? Crumbles it, puts cracks in it, makes the whole thing... anything you build on top of it less likely to be durable and to be accurate, is this inaccurate definition of the foundation. And the very fact that they keep saying this pull crap, it shouldn't be a word used. Just like random and spontaneous, these are not words that really should be part of the physics vocabulary, because it's a push universe.
Is going to be converted into other forms of energy. At first, it's going to be kinetic energy. Those gas clouds and dust clouds are going to be moving faster and faster, but eventually, as they get closer and closer together, those gas clouds are going to start rubbing against each other, running into each other.
They're going to gain more motion this way and less motion that way. That's what's going to change. So their velocity, rotating velocity, is going to start disappearing, and their velocity towards the center is going to start increasing.
Each other, and it's going to convert that kinetic energy to thermal energy, which means it's going to start to heat up. So again, we've got this spinning cloud of gas. It's starting to pull that material in. Gravity's pulling that material in, and it's starting to heat up and spin faster. Most of that material is going to fall right to the middle and heat up a lot. Some other little...
I don't even think this is the right explanation of how the gas starts to spin in the first place, because that's part to do with the randomness of collisions. So in real gravity, if you threw objects, in two directions, okay, what gravity will do, in the sense is those objects will inevitably all hit each other eventually, and they'll exchange. And the fact is, whichever side had more marbles is which side all the remaining stuff will move in that direction. So it takes a chaotic pile of energy and it converts it into one unified motion. So as all these little molecules hit each other in the gas cloud, as they're spinning, they don't start off spinning. They only end up spinning because there is in fact more momentum just by chance in one direction than there is the other. It wasn't just there wasn't a perfect symmetry in the circumstance, and so unless it's perfectly symmetrical, then you could have some circumstance where there's no rotation. But there's always going to be one side that's stronger than the other side, and there's going to be some rotation in that direction.
Bits of that material might end up kind of spinning around and starting to clump together on its own. And notice we're already making a pretty decent solar system. That majority of the mass that falls in towards the center, that's going to be a star. It's heating up. Eventually, it'll be the right conditions for fusion to initiate in the core. And the spinning stuff that didn't quite...
So this is just a clump argument or a pearl and an oyster argument or something. You have to have some reason why everything goes towards a center. So there has to be more mass in some sort of area for everything to clump towards that one mass eventually. But yes, that's the rule. The biggest person wins. So whatever this blob of crap I have, wherever I put the heaviest piece of mass, that's going to end up being the center eventually.
Fall in, well, that's going to be the seeds of planets. That's going to be the precursors to planets, asteroids, comets, things like that. So the point that I want to make here is these ideas in terms of conservation of energy, Newton's laws, angular momentum.
So none of that crap. Anytime you say kinetic energy, you're really not talking about Newton's laws in a way, okay? Especially the kinetic energy is 1/2 mv squared. That's not Newton's laws. Newton believed there was a direct and clear equality between something called a force and momentum. Force and momentum were essentially exchangeable objects. If you wanted to have twice the velocity, twice the movement, as Newton would say overtly, if you want twice the movement, apply twice the force. They're perfectly equal to each other. They're perfectly synonymous with each other. It's all just momentum. So don't really use Newton's words and Newton's as an idea if you're not going to be honest and describe what Newton believed in. And everything about modern physics is an offense to everything Newton believed in, because you think kinetic energy rules the particle universe, and he knew that momentum rules the particle universe. So it's just a real slander against a dead guy to pretend he was on your side. He wasn't. He opposed this religion when it was invented. And so quit pretending he's one of the fellows of your religion, one of your disciples, because he's not.
These concepts are going to be coming up again and again throughout the course. So when we eventually get to talking about the finer details of things like star formation or, the properties of stars, properties of galaxies, things like that, these ideas are going to keep on coming up. So we'll call that good for this session, and hope everyone's doing well.
Blah, 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 blah. So anyway, again, he's pretty much pointing out how he's doing some sort of teaching here. And, I'm just going to argue that they haven't written the teacher's book yet, so they really shouldn't be teaching what they haven't figured out, and they really haven't got a rational model. They got this stupid bent space that moves the same speed as the other forces, which doesn't make any sense just by coincidence. Gravity moves the same speed as a photon. A photon isn't bent space. Okay, it's supposed to be a wavicle. The whole idea of, again, creating this, entanglement and superpositions and all this mush out of a simple little two-slit scatter experiment. It's just pathetically bad physics and poorly reasoned. It's illogical, and again, they just cheat the truth by implying it's verified by all the experiments and verified by Newton says so. Newton didn't say so. So that's just a big lie. Alright, so that looks like the video. No comments. No, insanely relevant comments. So it looks like I'm not going to be staying long. Alright, so we can get rid of that, I guess. I didn't get rid of it. Oh, I locked it. Yeah, I got to hit the eyeball thing. Alright. So I'll give you a couple of minutes, and then we'll toddle off. So again, I just want somebody to just point out how when you have a time-dependent force, 9.8 meters per second, how it's rational, okay, to measure how far distance. How distance tells you how much force there is when it's a time-dependent force, and you could obviously vary how fast you move the distance. Point out how the bucket analogy of collecting gravity fails. Point out how something could have 4 times the energy and only weigh twice as much. That would be a good one, right? Just explain how something can only weigh twice as much, but it has 4 times the energy. I mean, it hits something with a weight. How, again, how compressing a spring twice as much requires 4 times the energy, when all it requires is 2 units of work. I should see how many people are in the room. Is it Friday? Yeah, Fridays are a tough day, I guess. Everybody's already off vacationing or something, I guess. What am I looking for? I'm looking for the live thing. There's the live thing. 13. Well, 13's enough. You should be capable of generating some relevant commentary, some insightful statement. Sorry I'm late. Did I miss anything? Yeah, the whole video. Yeah. Hello. Well, hello just doesn't do it for me. I'm sorry. I know it's a nice pleasantry and all that. How you do, and I could ask you how you're doing, and then you could tell me, well, I just got diagnosed with incurable, brain rot disease. And I'd say, oh, I'm so sorry. And I would be sorry, but it was just like, oh, shit. Ew. Yeah, so, yeah, I'd rather avoid those kind of conversations, actually. Yuck. Let's see, YouTube notified me late, I guess. Well, who knows? Could be. I watched yesterday's video after the event and saw you talking to me. Yes, well, I don't know. I guess I talked to you in some comments somewhere. I don't know exactly. I don't know. I don't know what to say. I mean, I think I talked to the comments as they come in, so, but whatever. No. Good news is I don't remember what you said. I'm sure it was stupid and I hated it, but whatever. I'll forget. I saw a video, what is this? Oh, Jesus. Slander you recently that was posted an hour ago. Okay, that doesn't tell me much. You could tell me what channel it's on. But there's nothing new about the slandering part. So, channel of the video. Channel name. I don't want to mention it on here. Well, yeah, it ain't gonna matter. You've already gotten people's curiosity. Oh, it's that guy. Oh, okay, never mind. Okay, so it's Farley or whatever it is, Goffeld or whatever the fuck his name is. So, yeah, I don't bother. People who can't even figure out the tiniest of common courtesies, I don't bother watching those videos. I mean, anybody who is watching those videos who can't figure out they're watching a video by a scumbag, those people aren't going to be able to do any physics. I mean, the very fact that you see the video means you must be subscribed or something, or it's in your feed or something. I don't know. I'd sort of say bad on you. But I understand people's curiosity, so people are just curious. They want to see what happens. They're drama whores. So they go for that crap. But again, it's not bad on me. Bad on them. Let's see. Moore's hay. I don't know what that is. Oh, he said hey. They're saying hey to each other. Hey. I'm going to have to put this in the pathetic commenting category. Pathetic chat, yes. So I'll make a folder and I'll put the pathetic chats in the pathetic chat folder. Alrighty then. Running out of time, people. Physics. Say something physics relevant. How's the weather for everyone? Oh, you're just being such a asshole. It's raining here. We're just cold and dry here. It just rains and then it doesn't rain for 2 weeks. It's really a pain in the ass having a garden when it doesn't rain. Yeah, what are the Mets doing? And such. Yeah, it's funny. When I think about, I used to be capable of being entertained by actually watching a baseball game. It was kind of funny in the past. And I can see the psychology of it in retrospect because I always just had some player I sort of rooted for, and you just want to see if he could succeed and win and do all that kind of crap and blah blah blah, and it's just funny that it's just, I find it almost laughable that I could play such a silly, my psychology was so trivial that I could give a shit about something so stupid. I mean, I could be caught up in a lame, crappy soap opera. I mean, ooh. Did you hear that new popular music song? It slaps. No, I didn't hear it. I don't think much of modern or popular those aren't like really good words for music. Yeah. You don't look in the modern and popular category. I don't think you'll find music in that category. It slaps. I don't know what that is. Did you hear the new piece by Beethoven? Anyway. Actually, I saw a guy who did one of these modern versions of Beethoven, electric piano kind of. It wasn't even electric piano, it was other stuff and a piano. And, he sped the whole thing up and he did it, and it was, it really was an interesting reinterpretation, or interpretation. I guess it's a rendering, a redraw of a classic piece of music, and it, you'd almost say, just because of the added complexity, that it was better than the original. Even though the original seemed like it had all the pieces, this seemed to add just the right new pieces. So that happens now and then. But it doesn't happen as often as it should, that's for sure. They certainly haven't improved on Newton with their physics. Yeah. No, they sure have made a bad song out of it. Just a pile of noise. Little unicorn love songs. Oh, the singularity and the entanglement and the superposition all bending towards me. La 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 la. In the pull universe. Pull, 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 pull. Push is bad, 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 bad. Wavicle, wavicle. Ugh, it's really just a pathetic song, really. Pathetic. All right, so I guess I have to really go because you're people just you're just not going to play along at all, are you? You're just not going to perform your half of the duties here. Show me how dumb you are. Ask a really stupid question. Provoke me, trigger me to re-explain because you're a moron. Alright, so we'll just give up. Alright, so till the next time and such. Appreciate the participation, although I don't appreciate it much. Yeah, it's not a lot of appreciation. Kind of a minimalist appreciation this time, I have to say. You people have failed me. But anyway, till the next time and such and so forth and whatnot.